The Sun has entered its red giant phase, an immense overheated plasma sphere swelling outward. Mercury will be consumed first, then Venus. Ultimately, the Sun will expand close enough to render Earth uninhabitable. Even now, surface temperatures climb toward scales that sterilize the planet. This is Earth 5 billion years from now. But how did we arrive at this endpoint? Let's travel forward in time, from this very moment you're watching all the way to that distant day when the Sun is far larger, far brighter, and far too close for comfort. Over the coming centuries, the world will change in ways both familiar and astonishing. The next 100 years will likely be among the most volatile and consequential in human history. Breakthroughs in artificial intelligence, climate mitigation, medicine, and renewable energy will reshape our societies and economies in near unimaginable ways. But thinking in terms of centuries is still local. To understand the fate of life on Earth, we must think on a truly cosmic scale. Every place on our planet, every backyard, will eventually be incinerated. Within the next decade, humanity will dispatch probes to distant worlds and moons such as Venus and Europa, and we will return people to the lunar surface, including expeditions to the lunar South Pole. Within 50 years, it is plausible that humans will maintain a permanent presence on the Moon and begin sustained exploration of Mars. Over the following centuries, permanent settlements will form on Mars. Tens of thousands of settlers, accompanied by robotic systems and synthetic companions, will live and work beneath engineered domes and on reworked landscapes. Meanwhile, ambitious programs on Earth will attempt to restore global climate equilibrium. On Mars, the focus will be long-term planet-scale modification, thickening the atmosphere, raising temperatures, and producing liquid water in order to establish a sustainable greenhouse effect. Beyond the inner system, our search for life will reach a turning point. The ocean worlds, Europa, Enceladus, Titan, and Triton, will be investigated in depth. Should any form of indigenous life exist there, it may range from microbial communities to complex multicellular ecosystems. By the mid-third millennium, large-scale engineering projects will succeed in transforming Mars into a broadly habitable world. Planetary scientists, chemists, engineers, biologists, and computer scientists will apply technologies we can only begin to imagine. Advanced materials, autonomous manufacturing, planetary climate engineering, and artificial magnetospheres to address Mars's lack of heat, atmosphere, and magnetic shielding. The result will be a Mars where humans, transhumans, and machine-augmented beings can traverse open landscapes under a robust, Earth-like environment. Human expansion will continue to encompass asteroids and the major moons of the gas giants. Coastal habitats and orbital settlements will multiply. Venus, once a hostile inferno, will be the site of cloud layer cities and perhaps long-term geoengineering campaigns aimed at atmospheric transformation. These projects will take centuries, but human lifespans and medical capabilities will have advanced substantially. By the 26th century, the average healthy lifespan may well extend into the 150-year range. As humanity's energy needs and technological capacity grow, so will its scale of organization. We will reach what theorists call a Type 1 civilization on the Kardashev scale, harnessing and managing the full energetic potential of our home planet. Wind, tide, solar, geothermal, biological, chemical, and nuclear resources, and distributing that energy across global infrastructures. Over subsequent millennia, perhaps between the 4th and 6th millennia CE, humanity will complete the terraforming of Venus and move to even more ambitious projects. Large megastructures, artificial habitats, and energy harvesting installations built at solar system scale. A Dyson megastructure or a network of habitats that capture a substantial fraction of solar output would represent a transition to Kardashev Type 2 status. Civilization capable of exploiting the energy of the sun. With interstellar ambitions realized, human descendants, whether biological, cybernetic, or hybridized forms, will move beyond the solar system. These beings will be adapted to life in low-gravity and high-radiation environments, aided by nanotechnology, genetic engineering, and machine integration. Human morphology may change dramatically. Taller statures in low gravity, altered vision for dim or redder stars, and bodies integrated with computational and defensive technologies. Yet technological advancement carries risks. The so-called Great Filter Hypothesis suggests that advanced civilizations can self-annihilate through misapplied technologies, runaway ecological collapse, or other existential threats. Some models propose substantial probabilities that complex civilizations do not persist beyond a few thousand to tens of thousands of years. a sobering counterpoint to our long-term aspirations. Assuming we survive these near-term existential hazards, Earth's long geological and astronomical future still presents major transformations. Over the next 100,000 years, natural climate cycles may drive the planet into a deep glacial period, unless countered by human engineering. Cataclysmic volcanic events, for example a major Yellowstone-scale eruption, could inject aerosols into the atmosphere, inducing global cooling and ecological stress. Across millions of years, tectonic drift will reconfigure continents. Supercontinents may form and break apart, mountain ranges will rise and erode. Phobos will decay and disintegrate into a faint Martian ring. Impact hazards remain a constant. Large near-Earth objects could trigger mass extinctions unless robust planetary defense capabilities are in place. On timescales of hundreds of millions of years, nearby massive stars and exotic stellar systems pose threats. A sufficiently close supernova or gamma-ray burst could strip Earth's atmosphere of ozone and precipitate major extinction events. Defending against such energetic astrophysical phenomena would be a profound technical challenge for any civilization. By 1 billion years from now, the sun's gradual brightening will have serious consequences for Earth. Increased solar luminosity will alter atmospheric chemistry, disrupt the carbon cycle, and drive oxygen levels down as photosynthesis becomes unsustainable. Most oxygen-dependent life will perish. Only anaerobic organisms will endure for a time. At that stage, habitable zones in the solar system will move outward. In roughly 2–3 billion years, the Milky Way will experience significant interactions with neighboring dwarf galaxies, and on cosmic timescales, the Andromeda-Milky Way interaction will reshape stellar neighborhoods. Galactic dynamics combined with stellar evolution will lead to further instability in local star systems. Finally, about 5 billion years from now, the Sun will exhaust the hydrogen in its core and expand into a red giant. Its outer layers will engulf the inner planets. Whether Earth is swallowed outright or survives as a scorched remnant, conditions will be far beyond the tolerance of terrestrial life. Habitable real estate will have shifted to the outer system and to engineered habitats, moons of the gas giants, artificial constructs, or interstellar refuges. If humanity, or its descendants, are to persist through these epochs, they must become a truly spacefaring multistellar species. Survival will require mastery of planetary engineering, stellar-scale energy systems, robust defenses against astrophysical hazards, and the adaptability to evolve or redesign life itself. Can we make alien worlds habitable? Perhaps. The technologies and social will required are vast. The story of how we build them, and whether we choose to pursue them, will determine not just the fate of our species, but the destiny of life in this region of the cosmos. This is the long view, a sequence of profound opportunities, brutal challenges, and epical transitions. The Sun's red giant future is inevitable on astronomical timescales, but the path humanity takes between now and then, whether toward extinction or cosmic resilience, depends on decisions we make across generations.